Thank you for your introduction. And it's my great pleasure to be here to talk about locating arrays in this conference and the celebration of Charlie Copen's 65th birthday. Happy birthday! So actually, this topic was motivated by a talk in Hangzhou, maybe one and a half or 2 years ago by Charlie in a conference. And in that talk, he introduced the concept, the notion of locating arrays and detecting arrays. And at the moment, we noticed that when we take some considerations about the errors of such kind of test problems, so what happened? And this becomes this research. So this is a joint work with Professor Masato Jimbo in Tsubu University. Okay. Oh, okay. It works. So first, let me introduce illustrate a simple example about how this kind of works, this kind of things works. But I think probably in the first day, Professor okay, sorry. I think he has gave a brief introduction and or concrete introduction about this problem. But I will speak about this thing from the very beginning. That is, if by an example of the application of software testing, for example. Okay, it's okay. Thank you. Now we consider such kind of application that we assume that some applications, some applis are installed on PC or your smartphone or something else. We assume that there are K applications installed. And now another assumption is each application has two status with the status 1 and status 2. And maybe some status of the application may cause a fault of the system, either a PC or smartphone. So for example, if we consider only one status of the application, then we represent this kind of things by the application and its status. And if there is a combination, that is, when these two status meet together, then there will be a fault. In this case, we consider the combination, a pair of such kind of things. So in this case, if we only consider one, then we call it a one-way interaction. If we consider a combination of a pair of such things, we call it two-way interaction, and so on. So the purpose of this research is to, how can I find such kind of faulty interactions? And in order to find such things, we introduce the text suits. For example, this kind of things, we call it is a text suit, and it is naturally represented by an array whose entries are the status from this symbol set, that is 1 or 2, and each row corresponds to a test, and each column here corresponds to some applications. And in the terminology of interaction testing or design of experiments, we call this is a factor, and each symbol corresponding to a fixed factor is called a level. So here are the terminologies. Essentially, the terminologies we use is totally the same with that used in the designs of experiments. And this set is called factors and levels. And here we consider the pair of levels, the factors and levels by a subset. Then such kind of T subset is called a T-way interaction. And the test is actually a k-tuple index by factors. and the coordinate indexed by f has some entries in the status in the level set. So a text suite is just a collection of such kind of tests. And also, we have just heard that it is natural to use an array to represent the text field consisting of n tests with key factors. So the problem is, first we need some assumptions that first, each test will give, when we employ such kind of test, we will get an outcome. Say 0 or 1. 0 means there's no problem, and 1 means there may be some faulty interactions in this text. So another assumption is the failures are caused by an I-way interaction with I at most t. And the main problem is there really some I-way interaction causing some force? And the second problem is, how can we identify, how can we point out which are they? And the third problem is the main problems in combinatorics, that for given number of factors and the number of the T of T-way interactions, so how many tests, that is how large the number of tests are required. So actually there are some combinatorial arrays and which attracted Charles several attractions in this research, that is covering arrays. This keyword appears in the first day several times, I think. So, but the covering arrays just require that all I-way interactions are covered by the text fields. And so in 2008, I think, in the paper published in Journal of Combinatorial Optimizations, they introduced the notion of locating arrays and detecting arrays. Now, in this talk, we mainly talk about the locating arrays. That is, for example, also an example, if we consider this kind of text field, after a round of tests, for example, if we get such kind of outcome which shows that the test 1 and test 2 give some bad result. That is, maybe here some one-way. Now we consider some one-way interaction. That is, we only consider one symbol in this array. So that means this line give a bad example. This row give a bad example. So the outcome tells us that this T1, T2 contains some 41-way interaction, and the others do not. So how can we find the bad guys? Now we can see that for the F3, here is the 3 and here is the 3, so they are in common, and this 2 and this 2 are in common. But there's another 3. F3 also appears in T6, but T6 tells us this is not bad. So we can say F6 with level 2 is the bad guy. So by using a formulation, we can say that we use a symbol row of this F6 and 2 is the text T1, T2. So here is another example. So now the outcome has been changed. Now, if the outcome tells us T3 and T4 give bad results, so what happened? In the same manner, we can see that F2 and 2 are here only in these two tests. And also F9 and 3 only appears in these two tests. So, which is bad guy? We cannot identify the unique one. So in this case, by formulation, we can see the row of F22, that is all the rows containing this one is T3, T4. Now also, if we consider F9 and 3, we get the same subset. So this is a problem. And in general, we can say, if for distinct one-way interaction, T, we consider the row of some T and some T prime If they are never coincide, then this tag suit can identify a unique bad guy by using such kind of test. So here we introduce the definitions of this kind of things. So here we use the symbol. We use the symbol A to be the arrays, and K to be a T subset of the column indexes for A. And that means this for T cap, and here we consider some T-way interactions denoted by T, and we use the symbol rho of this array A of some interior interaction T to be the subset of the row indexes in which the T-way interaction appears in all of those tests. So how can we find the force? Now, first, let the script T be the set of I-way interactions, and assume that there is only one I-way interaction that causes the failure in T. Actually, there is a more general definitions which considering some more interactions. And here we just assume that there is a one I-way interaction. And array A can be locate any single failure in the script T if and only if the supports of these row indexes are distinct for each T-way interactions. So such kind of array is called a T locating arrays. And here another exception is we'll only consider one interactions. So in the way we're familiar with, that is, we can represent such kind of arrays satisfying the property T locating property by using a set system. That is, if we consider every factors and every corresponding levels in this way, and here we write the row, for example, F1 here to be a subset of the row indexes, then we can see here is a set system that is actually containing of all the rows for all the one-way, here in the example, one-way interactions. And each row just form a partition of the, here is the set from 1 to 6. So the key property is every subset in this table should be distinct. And this kind of things, because here is some partitions, this is also regarded as a spread system. Here are some 9 spreads on 6 points, and with each spread with 3 parts. So now, there are 2 similar words in this part. That is, we have a fort and also error. Maybe as a simple word in English, it's a similar meaning. But force means the bad guys they give the bad outcomes. And error means if we consider the outcomes, so maybe the outcome should be 1, but it gives 0. Such kind of things is called an error. So now, for example, the outcomes give us the first test, and the first test give the bad outcome. But in this case, maybe this subset 1, 4 does not fit any supports in the previous table. And in that table, actually, the 1, 2, 4, the subset is the nearest. It means the nearest means it has the smallest timing distance in the term of coding theory. So in this case, maybe we can say that there may be 1 error, and the correct answer may be 1, 2, and 4. So in this case, actually the minimum distance, we should consider the minimum distance of this subset in the table, and also in this case, all one-way interactions can be detected even if can be detected also can be corrected, and most one error in these outcomes. So in this example, we can see in this table there are such kind of subset. This is nothing but here is a standard triple system, and I think everyone's familiar with. So if a t-locating array tells us some E arrows, namely even if the outcomes at most E arrows, the t-locating array still, the t-locating property still holds, then such kind of array is said to be an E array locating E array fraction t-locating array, or simply t-locating arrays. So the main problem is for fixed t and some E with s levels, that is number of symbols, and k factors, how can we find the minimum number of tests? Or conversely, if we given the number of tests, how do we find the maximum number of factors in this table, in this array? So we use these two symbols to represent the bounds. And okay, so actually there's not many unknown for such kind of bounds, even if we consider no errors. For example, here is a bound provided by Tang, Kuben, and in their ASPI paper, I think. So here looks complicated, but actually this is very efficient when the number of factors is not so large. But actually, when the number of factors is large, we can simply consider by counting the number of subsets, and just by counting subset, and so we can get, by using the definition, we get the simple bound. When the k is large, the simple bound may be better. So also we can use the idea by the TC-wise bound to get the improved bound by here, and when k is large, it also works well. So we can just set in taus 2 or 3 in this formula to get their bounds. And also here for the case when we don't consider errors and we consider t is 1, that is one-way interaction, there's a perfect solution for the one locating arrays that this is a science discrete math paper by Charlie Coben, Professor Fan in Beijing Jiaotong University, and Daniel Housley. They developed this theorem as an analog of the well-known Baldwin-West theorem in the hypergraph theory, and they completely solved this problem. So here, if we consider the error corrections, and in the case of one-way interactions, actually by using some very well-known bounds in coding theory, that is the Hamming bound and Johnson bound, to consider like a code word of a code. So this is some simple approaches where we consider only one-way interactions and some errors. And here, by using some well-known codes, we know, for example, if we consider a binary linear code, if we remove the zero element, the zero vectors and all one vectors from the code words and consider the parts of the code words and the supplementary set of the code words, then this forms that actually this is the optimal binary 1D locating arrays with n text and 2 to the powers k minus 1 factor. So actually, if we consider Hamming code, then we can get a equality of such kind of bound. So this is a simply application of this construction. And also another approach, as I say, is also in the research of covering arrays, the Paley type matrix is also is commonly used to construct such kind of things. So here we consider the Paley matrix, that is the incidence matrix of Paley graph. Here we consider the order to be prime 11, and we get such kind of matrices. And a little bit different is we define the elements in the diagonal to be 1, and it is identified to the case when this is non-zero, non-square. So actually, there are some generalizations of the Paley type matrices. That is, we not only we can consider the particular residual, we can also consider some other the multiplicative characters, and to define the Paley-like arrays with non-binary matrices, or some S-array matrices. So by using the calculation of the character sums, we can show that for any given S and T and some error T and E, there exists some Q by Q array that is a S array T LA when the order or the size of matrix Q is given large enough. So here is some concrete example we calculated for the small cases. For example, when we consider the binary cases, and we consider the case when T is smaller 1, 2, or 3, we can calculate like this. And the errors correction is just in this form. So what I should be noticed is, this is remarkable to say that actually a Paley type matrix has been used to construct a T allocating arrays for any T, any given T, and for sufficient large Q, this also holds for a T allocating array. And also, if you consider a T plus 1 covering array, then this is actually also a T locating array. So it's not surprising that the Paley matrices give us the construction of locating arrays, but maybe it is a little bit hard to evaluate the concrete numbers of the error correction abilities for covering arrays or something like that. So here we do a concrete calculation for this kind of thing. But this result is not so surprising. And okay, so the last word I should say that is actually, if we consider some other probabilistics method, it will help us to determine some better bounds of such kind of things. And also for the Paley matrices, we can truncate the rows from the matrices to get some more small matrices. So such kind of result is like this. Here is the number of factors, and the red ones are the truncated matrices of the number of the rows of the matrices. Here are some computer experiments, so the curve looks not so beautiful. Okay, so I should stop here, and thank you for your attention.
Thank you, Xiao-Nan. There is time for a very quick question. Remarks?
Well, instead of Paley,
Yes.
you could take, instead of, the Paley is the logarithm of the field element mod 2, essentially. You
Yes.
could do mod some other V's.
So actually, this is this is what I cite for the general cases.
Pardon me for missing it.
Yes, this is the case when this is not binary.
Yeah, pardon me.
Okay.
Thank you, Xiao-Nan.
Thank you.